Hello everyone, welcome to the series of lecture on lipids. So today I will be discussing to you the part 1 of this lesson on lipids. So welcome to this video presentation. So lipids are another group of biomolecules, major group of biomolecule that is very important, and they are commonly found in living organism. It says here a lipid is an organic compound, and the characteristic one of the characteristics of lipids is they are insoluble, or we could say that they are sparingly soluble, and they are water insoluble but soluble in nonpolar solvent. So we have to distinguish the difference between polar and nonpolar solvents. Polar solvents include water and alcohol. Nonpolar solvents include benzene, hexane, carbon tetrachloride, and many more. However, it says here some lipids could be sparingly soluble in water due to the presence of other functional groups, but some lipids are totally insoluble in water. All right? Lipids can be categorized into the following based on their function. There are so many kinds of lipids and their structures vary. That's why it's easier to categorize lipids based on their function. So we have energy storage lipids, and that includes the triglycerol. Membrane lipids, which includes the phospholipids, sphingoglycolipids, and cholesterol. Emulsification lipids, which include bile acids. Chemical messenger lipids includes the steroid hormones and eicosanoids. We have also, last but not the least, the protective coating lipids. Example is biological waxes. So we will study these 5 categories of lipids one by one. The component, the basic or the simplest unit or component of triglyceride or triacylglycerol. Remember, the one of the classifications of lipids is the energy storage lipids. That includes the triacylglycerol. Okay, so let's begin with the first classification, the triacylglyceride. Okay, or triacylglycerol rather. Triacylglycerol. Okay, let me just erase this. Let me just write triacylglycerol. Or in this lecture, I will be using a shortened version of triacylglycerol. I'll just call it TAG. So the first classification of lipids is based on function is energy storage, and that includes TAG or triacylglycerol. Now, TAG or triacylglycerol is composed of fatty acids. Okay? TAG is composed of fatty acid. Okay, I will show you how TAG is formed later. So, fatty acids or fatty acid is a carboxylic acid with linear carbon chain. Remember, a carboxylic acid, just like what you have learned in organic chemistry, a carboxylic acid has a general formula. Let me just write here. Carboxylic acid has a general formula of R, C, double bond. This is a carbonyl group. But attached to this is an OH. Okay. So, carboxylic acid is a weak acid. The presence of this hydrogen makes the carboxylic acid acidic. So this is the general formula of carboxylic acid. So these are, remember this is, it says before in the previous lecture, an R is the rest of the molecule, and it denotes the carbon group. Okay, so right here I have a structure of a fatty acid, and this section here, this represents a carbon, and this is the R group. Okay, notice that in this carbon right here, the oxygen is doubly bonded, and then I should put another oxygen. Sorry about that. I missed the oxygen. Okay. So this is our carboxylic group or carboxyl group, and this is the tail, or we can say this is the R group, the rest of the molecule. Okay, it says here unbranched carbon chain. So there are many carbon atoms so connected to this carbon. So this is carbon, another carbon, until this is the endmost carbon. I think there are 18 carbon atoms beginning from this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 19. I should erase one. Oops, I cannot erase. But anyway, there must be 18. In some cases, there are odd number carboxylic acid. So anyway, it says here that a carboxylic acid has a linear carbon with a carboxylic group. Okay, this is the carboxyl group. Okay, and usually they have even number of carbon atoms. But in this illustration, there are 19. But it's okay. You can just normally even number, but there are some cases that there are odd number, but it's very uncommon. Okay, normally they have even number of carbon atoms, and they are classified or categorized into long chain, medium chain, and short chain fatty acids. Now, fatty acids may be saturated or unsaturated. So remember, in your organic chemistry, I reviewed to you, I gave a lecture on the difference between saturated and unsaturated. When we say saturated, the carbons are single bonded all throughout, and then in unsaturated fatty acid or unsaturated molecule, you know that there are carbons with one or two, there are carbons with double bonds. Okay, so saturated says here all carbons are single bonds. Okay, and to number the carbon, okay, to number the carbon, we begin from, numbering starts from the end of the carboxyl group. Okay, say for example, we have here 2. Okay, so let's write here. This is the carboxyl group. Okay, and remember there's one carbon here. This is the carboxyl. Okay, this carbon becomes your carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, 11, and 12. Okay, this is the 11th carbon and this is the 12th carbon. Okay, so this fatty acid is called lauric. It's called lauric acid, and the number notation is 12 colon 0. 12 colon 0. 12 means there are 12 carbon atoms, and then 0 means there is no carbon to carbon with double bond. Alright, so that's how we write fatty acid. That's how we draw the line formula. Remember, we don't put the hydrogens anymore because it's understood that each of the carbon has their corresponding number of hydrogens. Okay. Unsaturated fatty acids, there are carbons with double bonds. A mono unsaturated has one carbon to carbon double bond. And polyunsaturated fatty acids, there are 2 or more carbon double bonds. Okay? So here, in this illustration, in this picture, there's only one carbon to carbon double bond. If I'm not mistaken, there are 18 carbon atoms here. Okay? The name of the fatty acid, is oleic acid. Oleic acid has 18 carbon atoms. And if you write the number, if you assign number, this becomes 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? This carbon with double bond is the carbon number 9. So we write 18 colon. Okay, we write 18 colon 1. Okay, that means there are 18 carbons, 1 double bond, and we write delta 9. Okay, this delta 9 meaning the double bond is on carbon number 9. So that's how we write the number notation of oleic acid. Okay, once again, this fatty acid is called oleic acid with number notation 18 colon 1 delta 9. 18 carbons, 1 double bond on carbon number 9. Okay, so this is called monounsaturated fatty acid. Now, right here, there are examples of polyunsaturated fatty acids. Okay, they are called PUFAs, namely lenolenic acid, lenoleic. Okay, this is lenoleic, eicosapentaenoic acid, arachidonic acid, and docosahexaenoic acid. So you notice that in lenolenic acid, there are 18 carbons, okay, 18 carbons, 3 double bonds, okay. Lenoleic acid, all right, lenoleic acids, there are 18 carbons, 2 double bonds, all right. And as you can see, in eicosapentaenoic acid, there are 20 carbons and 5 double bonds, and so on. Lenolenic acid, the number notation is 18:3, but if you are going to assign the number of carbon atoms, that would be in carbon number. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 18 carbons, colon 3, delta, we will assign delta 9. Okay, 9, 10, 11, 12. So delta 9, comma 12. Okay, 13, 14, 15, comma 15. All right, so 16, 17, 18. So there are 18 carbons, 18 carbon atoms, 3 double bond on carbons 9, 12, and 15. So you separate the numbers by a comma. Okay? For linoleic acid, there are 18 carbon atoms. Okay? 2 double bonds on carbon number 9 and 12. Okay, so let's write here delta 9, comma 12. Okay, so find out for the rest of the molecule for eicosa pentaenoic acid, or this is known as EPA. Where are the double bonds? Okay, DHA. This is usually you will encounter DHA as a component of milk formula. All right, so DHA has 22 carbon atoms, 6 double bonds. You assign the delta or the position of the carbon double bonds, carbon with double bonds. Okay, it says here omega, or actually this is an omega 3 fatty acids. So these three, the linolenic acid, EPA, and DHA, they are called omega 3 fatty acids. And these two right here, these are the omega 6 fatty acid. Okay, omega 6 and omega 3. If you are asked what are the omega 6 fatty acids, the linoleic acid and arachidonic acid. So what are the omega 3 fatty acids? Linolenic, EPA, and DHA. Okay, once again, the numbering begins or starts at the carboxyl group. This is the carboxyl group. Remember that that becomes your carbon number 1. Okay, this is carbon number 1, and then 2, and so on. So this is the endmost carbon. The double bond is on carbon number 6. That's why the number notation is 18, followed by a colon 1. That is the number of carbon at the number of double bonds, and then delta 6, meaning the double bond is on carbon number 6. Now, there are what we call omega acids. Okay, just like what I have shown you earlier, these are the omega 3 fatty acids, and these are the omega 6 fatty acids. Okay, omega acids, some of them are essential. They must be part of the diet. Essential, when we say essential, part of the diet because we cannot synthesize them. Essential, they are needed by the body, but we cannot produce them. We cannot synthesize them. Okay, that's why they must be obtained from the diet. The question is, why are they called omega acids? Okay, so let's talk first about the omega-3 fatty acids. So when we say omega means last or end. Okay, remember this is the carbon number 1. Okay, that's the start or alpha. Let's say just start carbon. Okay, starting carbon, and this is the omega carbon, the endmost carbon. Now, when you say omega-3 fatty acid, you will count beginning from the last, from the omega carbon. Okay, you will count or how many carbon atoms you will encounter from the endmost carbon, from the omega end, from the omega tail. Okay, so this is beginning from the omega. This is 1, 2, and 3. Okay, beginning from the omega, there are 3 carbons including this carbon. That's why omega-3. Okay, in eicosapentaenoic acid, in EPA, this is also omega-3 fatty acid, because likewise this carbon is the third carbon. This is the third carbon from the tail, from the omega carbon. So 1, 2, 3. Okay, for DHA, again, this is the omega carbon, and then this is your carbon number 1, 2, and 3. That's why omega-3. Omega-6, the same principle, but you will count the number of carbon atoms including this. So this is 1, 2, 3, 4, 5, 6. So you will encounter the double bond beginning from the endmost carbon. So for arachidonic acid, 1, 2, 3, 4, 5, 6. For DPA, 1, 2, 3, 4, 5, 6 also. So that's how we assign numbers for omega acids. If you have margarine or margarine, you notice that margarine stays solid even at room temperature. However, there are some oils, let's say olive oil or some vegetable oil, even if you put in cold temperature inside the fridge, or even at in the grocery where the temperature is low, the oil remains liquid, while margarine, as I said, solidifies at room temperature. Okay, that the reason, okay, the reason for that is that depends on the number of carbon atoms and the number of double bonds present in the molecule. So it says here the melting point. Okay, the melting point depends on the number of carbon chain and then the number of double bonds present in the molecule. It says here um, the melting point is determined by the chain length and degree of unsaturation. Increase chain length, that means the longer the carbon atoms, the higher the melting point. The higher the degree of unsaturation, meaning the more the double bond present, the lower the melting point. Look at this table. The fatty acid that contains 16 carbon atoms, 16:0, meaning this is saturated, no double bond. Okay, and if you compare that with 18 carbon atoms, both of them are saturated, but this fatty acid has longer carbon atoms, and it exhibits higher melting temperature. The 16 carbon atoms exhibits 63.1 degrees Celsius as its melting temperature, while this fatty acid that has 18 carbon atoms exhibits higher melting temperature. Okay, melting point 69.6. But if you compare these two, okay, the presence of double bond decreases the melting temperature, the melting point. So if you compare, okay, this is saturated, okay, this one is unsaturated. The unsaturated, the melting temperature is very low, 13.4 degrees Celsius. It says here the reason why unsaturated fatty acid has low melting temperature, because the number of bonds in fatty acid increase as the number of carbon atoms, the number of double bonds increase. So the double bonds, okay, the double bond in fatty acid, okay, listen to this. The double bond in fatty acid creates what we call bends. Okay? And the number of bends in the fatty acid increase as the number of double bonds increase. So the more the double bonds, okay, the more the bends. Okay? The more bending. Okay? Bending, something like that. Because when we say saturated, okay, that's right here, saturated fatty acid, they are linear, okay, straight, whereas unsaturated fatty acids, they are not linear, they have what we call bends, okay, or the molecule, the fatty acid bent, okay. So the more the double bonds, the more bends in the fatty acid. As a result, less packing, okay, less packing occurs, melting temperature is lower, and the fatty acids tend to be liquid at room temperature. All right, that is the reason why they have low melting temperature. Fatty acids can also be in the form of cis and trans. Remember, cis and trans, uh, they are a form of geometric isomerism. Cis and trans isomerism. Okay? When we say trans, as I told you before in organic chemistry, uh, trans, that is the hydrogen atoms, okay, the hydrogen atoms in the carbons with double bond, okay, are at opposite direction, okay, that is trans. When we say cis, okay, look at these hydrogen atoms, the hydrogen atoms are at the same side, that is for the cis. Naturally occurring fatty acids are in the form of cis. Okay? Fatty acids can also be essential or non-essential. I told you earlier that non-essential fatty acids that are required by an organism but can be synthesized. Meaning, if we humans, we require this fatty acid, but we can also synthesize it. We can also make it. Okay? We can make it. We can synthesize it. That's why it's called non-essential. When we say essential fatty acids, an organism requires but cannot synthesize those fatty acids. That's why we must obtain them from the diet. Example of essential fatty acid is the lenolenic acid. Okay, lenolenic acid. Remember, this is an omega 3 fatty acid. Okay? We cannot synthesize this fatty acid. This must be obtained from the diet. Okay? So we are actually just discussing the first classification of fatty acid based on function. We are discussing the first classification of lipids, the energy storage lipids, or the triacylglycerol. As I said earlier, this is the TAG, or shortened as TAG. Now, TAG, okay, TAG is is a molecule. TAG is a molecule, or triacylglycerol is a molecule made from combining a glycerol and three fatty acids. Okay, I repeat, TAG is a molecule made by combining glycerol with three fatty acids. So this is the structure of glycerol. It's a molecule with three carbon atoms with three alcohols. Okay, three alcohols. And these are your three fatty acids: fatty acid 1, fatty acid 2, and fatty acid 3. You notice that the carboxyl group is right here. Okay, the carboxyl groups are right here. So the reaction between glycerol and fatty acid is called esterification. Esterification. Okay. So remember, in organic chemistry, as I said before, esterification is a process wherein you react alcohol. Okay, this is an alcohol plus um, a carboxylic acid. So your alcohol is the glycerol, and then the carboxylic acid is your fatty acid. Okay? So what you just have to do is combine the glycerol and the three fatty acid by removing this group here. This is actually water. So what happens is this carbon is now connected to this oxygen, okay, right here. All right, and then same process. This group here is removed. Okay, the carbon is connected to covalently bonded to oxygen. Okay, so same thing happens to the last fatty acid. By the way, this is what we call ester linkage. Okay, so there are three ester linkages here. That's why the process is called esterification. Ester, we formed ester. Okay, so a TAG, or triacylglycerol, is actually is an ester. Okay, so TAG is a molecule made by combining one glycerol and three fatty acid via esterification process. There are two types of triacylglycerol, or there are two types of TAG. Let me just say TAG to shorten. There are two types of TAG: um, simple TAG, and the other one is mixed TAG. When we say simple TAGs, the fatty acids are identical. Okay? The fatty acids are identical. When we say identical, um, the R groups, or the fatty acids, are uniform. All of them have, say for example, all of them have 12 carbon atoms. Okay, 12 carbon atoms, and yet they are all saturated. Okay, something like that, identical. Then we have also mixed TAG. or mixed triacylglycerol. A triester formed from esterification of glycerol with more than one kind of fatty acid. So just like what you can see here, in this fatty acid is saturated, while on this fatty acid here is unsaturated. So in nature, there are more mixed tags than a simple tag. Now let's see the difference between fats and oil. Okay, physically, under room temperature, fats are solid or semi-solid, okay, and they are predominantly composed of saturated fatty acids, all right? And when we say oil, the oils such as your vegetable oil, they are predominantly composed of saturated fatty acids, and normally they are uh, liquid at room temperature. So oil and fats, they are um, they are in the form of tag. Okay, both um, both oils and fats are in the form of tag. However, they differ in the presence of fatty acids. Okay, fats are tagged or triacylglycerol but are predominantly composed of saturated fatty acids. While oils, they are in the form of tag or triacylglycerol but predominantly composed of unsaturated fatty acid. Remember, as I said earlier in the previous slide, the presence of double bond. Okay, the reason why they are unsaturated because of the double bonds, and the presence of double bonds create what we call bends. Okay, bends. The bending in the fatty acid make the fatty acid to um, stay or to stay far from each other. So the presence of bending, uh, there will be less packing. Okay, that's why, as you can see here, the fatty acids are separated from one another because of the double bonds, because of the bending. So bending results into less packing, okay, less uh, intermolecular, okay, less intermolecular attraction. Okay, I repeat, the bending or the double bonds create bending. As a result, less intermolecular attraction. Okay, less interaction among these fatty acids. While a fat, which is predominantly saturated, okay, no bends, no double bonds, therefore no bending of the fatty acid. The 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 fatty acids tightly packed with one another. Okay, so we can say that more or greater, higher intermolecular attraction. That's the reason why fats are solid at room temperature. You need to add heat in order to separate the molecules, okay, the molecules of fats because of the tightly, okay, tight interaction of those fatty acids. Now let's go to chemical reactions. Chemical reactions of TAG or triacylglycerol. Okay? Um, the first is hydrolysis. Hydrolysis means breaking of bonds in the presence of water. Remember, a triglyceride or a TAG is made from the reaction between glycerol and three fatty acids. Okay, or a TAG is a molecule made by combining glycerol and 3 fatty acids. So this section here is the glycerol, and these are the fatty acids. Okay? So remember, the bonds that connect them is called ester linkage or ester bond. Okay? There are three ester bonds here. All right? So when we say hydrolysis, breaking of ester bond. In this case, what we are breaking is the ester bond. So breaking of bond in the presence of water. Okay? The hydrolysis alone does not or cannot take place, let's say, in our intestine, in our intestine when we eat food containing fats. The TAG or the triglyceride will be hydrolyzed in the intestine in the presence of enzyme. Those enzymes are called lipase. So lipase catalyzes breaking of ester bonds. Okay? So when that happens, when hydrolysis happens, the process or the reaction will produce glycerol and free fatty acids. Okay? When we say partial, there are only 2 fatty acids that will be removed to give rise to diacylglycerol and fatty acid. However, in this illustration, this is a complete hydrolysis. Complete hydrolysis, all fatty acids are removed. Okay, when we say partial, it's either 1 or 2 fatty acids are removed. Okay, complete hydrolysis, all fatty acids are removed. Okay, to form glycerol and free fatty acids. Saponification, okay, saponification is also hydrolysis, okay, but this is in the presence of basic solution. In the previous slide, in hydrolysis, what breaks the ester linkage is water. In saponification, what breaks the bond or the ester bond is a basic solution in the form of sodium hydroxide. So same process here, breaking of ester bond, but the agent what breaks the ester bond is the base or the sodium hydroxide. You can use any base, not only sodium hydroxide, can be potassium hydroxide. But the essence of this saponification is you are liberating the glycerol, okay, and you are forming a soap, okay, fatty acyl, sodium fatty acyl, or simply known as soap. All right, and then the third reaction is called hydrogenation. Hydrogenation is a process wherein hydrogen molecule is added to the double bond. Okay, that is to increase the saturation. Okay, so in this example, you have an oil. Remember, an oil is a tag that is predominantly composed of unsaturated fatty acid, but it can be converted into a solid, a component of, let's say this is component of margarine. Okay, remember a margarine is a solid. So an oil, to make a margarine, you need oil. But remember, oil is a liquid. It can be converted into solid by the process of hydrogenation, addition of hydrogen molecule. So the hydrogen molecules are added to the double bonds. So as a result, there will be no double bonds here. This becomes saturated. As I said earlier, saturated fatty acids, they tend to be solid, okay, because of uh, greater intermolecular or higher intermolecular attraction.